Our project of machine learning is recognizing faces in the wild. First is our introduction. The background of our project is kinship recognition is one of the hot spots in the field of computer vision. Kinship recognition has a lot of practical uses, such as helping the police and parents to find the lost children, providing auto photo management service, and so on. With the development of computer vision, CNN model is widely used in lots of computer vision works, and various types of architectures such as VGG and ResNet can be used in kinship recognition. The description is, our project aims to recognize whether there is kinship between two paired images. The following picture is our example. We explore and apply VGG face and FaceNet baseline models and try different ways to improve the model's performance on the FIW dataset. The second part is related work. We learn a lot from scholars' parallel work and read their methods and thoughts. Parallel work promoted kinship recognition with the help of image-based approaches and computer vision. They use machine learning techniques to extract facial features and train a kinship verification classifier on a collection of labeled images. For example, the first paper in automatic kinship detection was published by R. Fong in 2010. They select the most discriminative inherited facial features and use KNN to perform classification. The result shows that the proposed algorithm performs 4.9% better than human accuracy on this task. And this table shows scientists' parallel work in this field. Our work has several differences in comparison to parallel studies. In our project, we are going to learn different neural network algorithms for image recognition and approaches to measure the kinship between two people's images from different families. We are going to make a comparison between different models too.
In this project, we will use VGG Face and FaceNet as our functional API for model building. The API we get from the GitHub. First, I want to introduce VGG Face. VGG Face model is a face recognition developed by Google. The goal of VGG Face is to build large-scale face data science with minimal human intervention and train the convolutional neural network for face recognition. The network structure of VGG Face is basically the same as VGGNet, which contains 3 × 3 convolution kernel, and the convolutional step size is 1. VGG Face has a total of 3-4 connection nodes and doesn't use local contrast. Another face recognition is FaceNet model. FaceNet model could map the image to Euclidean space by convolutional neural network learning. Spatial distance is directly related to image similarity. Different images of the same person have a small spatial distance, while the image of different people have a large spatial distance. In our project, the image of person who have kinship will have small spatial distance. In our project, we design the two images are passed into VGG Face model and FaceNet model. We will remove the top layers of VGG-Face and FaceNet model. In this way, we could get the output is face embedding. These are our features. Then we will compute combinations of this feature, pass them to dense layer and softmax layer. We will submit the result to Cargo. On the Cargo, the evaluation is ROC and AUC. The ROC curve is a graph showing the performance of a classification model at all classification throughout. The ROC curve is a plot of false positive rate and true positive rate, and the AUC is the area under the ROC curve, and the AUC ranges from 0 to 1.
Next, I will show you the implementation of our project. Since the input of our work is a pair of face images, and then we need to distinguish their blood relationship, our designed DNA model is based on the semantic network. The semantic network has two inputs, and which will be fed into two neural networks simultaneously with sharing the same weights. These two neural networks map images into new representation space, where fx1 and fx2 encode x1 and x2 respectively. Finally, we evaluate the distance of the two inputs by calculating loss, and then get the probability that they have kinship. Below is the concrete architecture of our network. Firstly, we use features obtained from the pre-trained model VGG-Face. The VGG-Face model takes the input of shape 224 multiplied by 224 multiplied by 3. We remove the top layers of VGG-Face so that the output we get are face embeddings with size 248 multiplied by 1. We then use different combinations of features like square of x1 minus x2, square of x1 minus square of x2, and x1 multiplied by x2. These are concatenated and passed to full collected layer with ReLU activation and dropout prevent overfitting. Finally, we apply them to the softmax layer to get the probability of kinship. Inspired by extracting face features from the VGG-Face API, we came out to use the FaceNet API in Keros. Additionally, for feature embedding, we have to resize the input images to 160 multiplied by 160 multiplied by 3 before applied to FaceNet. The 128-dimensional advanced features learned from the FaceNet model based on a large amount of extra face data. We get the features x1 and x2 corresponding to image 1 and image 2 respectively. The features x3, x4 are generated from VGG-Face. Since these four feature embeddings have different dimensionality, we have to do a convolution to the distance matrix of x3 and x4. Apart from the three distance matrices mentioned before the DNA model, we changed the matrix to improve the complexity, like sine square root and other binary linear operations, and then concatenate x5 and x6, where x5 is combinations of feature x1 and x2, and x6 is the combinations of x3 and x4. Finally, we pass them to the two dense layers and softmax layers to get the probability of kinship. We are very happy to see we get a good result from proposed models. The accuracy of both models on train set are over 90%, and the accuracy on validation set. The foundation model is 0.07512, and the optimized model is better. We submitted our prediction of test set on Kaggle and get a record of the foundation model is 0.888, and the optimization model also get an improvement of log, which is 0.892.
In this part, I will give a conclusion of our work and talk about some ideas about future work. First, I will give an overall review about our project. Our intention to this project is to learn and explore how to carry out the task of kinship recognition, which is a hotspot in many areas. Basically speaking, we are supposed to give our judgment about whether people on the two images are from the same family and try our best to increase the accuracy of our prediction. We think that one of the most important tasks in kinship recognition is to extract the feature of those faces. According to what we have learned in MSBD5012, we focus on the CNN architecture because CNN is widely used to do feature extraction. During the study of CNN models, we noticed that the models developed by Google named VGGFace and FaceNight can be used to extract features of faces. Then we continue our work with the help of those two models. After contacting FaceNight and VGGFace, at first we selected VGGFace model as the baseline model, which is not good enough. Then we designed a SIMACE network as our foundation network, and we added the FaceNight model into SIMACE network. As a result, the performance of our model has been improved to some extent. Although it is not difficult to build the model because there are some references. During the process of model construction, we analyzed the network structure of the model and drew the diagrams to represent network, which helps us to better understand how the image data is converted into matrix and how the matrix is changed in the model. Then I'll talk about the future work. In this project, we use different combinations of features that are extracted from image to raise the accuracy. However, these combinations are selected randomly. There is no specific explanation about why choose such combinations. For further work, I think we can explore the mathematical explanation. Also, with the limit of time, we didn't adopt cross-validation, so we can train the model for different validation sites and then take the average of the predictions of all models. We also think that maybe we could do further work to detect who is the father and who is the son, which could be interesting. That's all for our presentation. Thanks.